Okay, so for this chapter itself, we're going to learn about your current of electricity. More specifically, we're going to learn about how and what is electricity itself, how do we calculate its individual components, how do we figure out which direction it moves, and so on and so forth itself. So the thing is, as you can see, there are some corrections, or there are some changes itself to the diagram. So if your textbook itself is using this version itself, do change the words accordingly. Scratch out the words that have strike off with red and then change it to the words. Because I realized that the words itself, they don't really correspond, how to say, they are not a one-to-one comparison. It's basically just vaguely linking them together. So by writing the words that are written here, you can see a much clearer side-by-side comparison. So on the left, you see you have a water pump, right? So you have this power source that's actually pushing the water, and then you have your water current over here. And just take note, this will be actually a constant flow. Okay, so let me just write down. There will be a constant flow. Okay, so you can see that after that, you have your obstacle over here. Now, do take note, what I mean by constant flow is when your current flows all the way through the entire system itself, this is constant throughout. It's the same flow. So you already already take into consideration the obstacle, which is your water resistance that is trying to stop your water from flowing. We already took it into consideration already. So at this point, your current and this point, your current, they are the same. Okay. So similarly, for your electrical circuit itself, you have your power source, which is your battery, and or a cell, okay, which we'll learn later. And then you'll notice that your current, you have this part, right? So this is also a constant flow of your electric current, and your electric current will flow all the way through the entire circuit itself. So you can see that at any point, the two arrows that you see, they are going to be the same current flowing through. And for this rectangle over here, this is your electrical component. But more specifically, we're just going to do a side-by-side comparison. This is talking about electric resistance itself. Okay, so this diagram itself is a little bit outdated. So I actually changed it to the more updated one where it looks like this. You can see a much clearer comparison itself. And you can see the resistance for the water is basically you have a thinner pipe over here. Okay, so because some students was asking previously is that, oh, Joe, how do I represent the resistance of this and that? Basically, you just have a thinner resistance. So same thing as well, if you have a very, very thick wire, if you have a thinner wire itself, you actually have more resistance as well. So if some of you are doing watching this online, you can actually just if you have the soft copy of the notes itself, you can just screenshot this and just paste it over. For those, if not, you all can actually take a post-it note and try to sketch this over your original text. If not, just wait for the updated version of the book. Okay, so we can see that they behave very, very similarly itself. So first things first, you'll notice that we actually use some of the symbols over here to represent different things. So first thing is your switch. So you have an open switch and a closed switch. Basically, you can just think of it as it's just a clip. So once your clip is closed, you are closed. If your clip is open, you are open. All right. The next is your light bulbs itself. Sometimes we call this a lamp as well. They are quite interchangeable. But basically, if the question says light bulb, use light bulb. If the question says lamp, use lamp. Okay. Then next, basically, it's just a circle and a cross itself. So make sure that the line don't cut through. Right. So if you ever need to draw this, basically you want to draw a circle and a cross, go through. Now the cross itself must touch the edge of the circle, because if you just draw like this, this is not a light bulb. That's just a belly button. Okay. So next is your resistor itself, and more specifically, this is a fixed resistor. Okay. Why is that so? Because this one have fixed resistance. Okay. It has fixed electric resistance. All right, we'll talk more about that later when we reach the resistance parts of the notes. Okay, so just take note of what is this first. And then you have your ammeter, very straightforward. You see the A. It's the A here. You see a voltmeter. Voltmeter is this. So you just circle with the symbol in the side. I'll talk to you about the function later. And then now, this part important. This is an electric cell. This is not a battery. A battery is a group of cells. Okay, so you have a singular, we call this a cell. If you have a group of cells, we call it a battery. You understand? So do take note about this. So battery is just a group of cells. And on the other hand, below here, you see this part, right? You have this variable resistor down here. So this means is changeable electric resistance. Okay, so just now we have your fixed resistance on top, and then we now have your changeable electrical resistance below. Okay, so do take note, the only difference between the two of them is that now you have this extra arrow here. Okay, so because of this arrow, you can just imagine that this is like a graph. You want to draw an arrow. So that arrow that you see is the gradient. So it must be a diagonal arrow. Doesn't have to be up, diagonally up, can be diagonally down as well. Because depending how you draw the draw the circuit itself, it looks slightly different from one another. Okay, so do take note about this. And sometimes you might see the word rheostat. Okay, this is basically the same as your variable resistor as well. Okay, so you can see below here, this is a very, very simple setup of your light bulb circuit. So let me just write down the names. This is a cell. This is a switch, and more specifically, it's a closed switch. This is your lamp, and this is a resistor. Okay, so how does your current flow? Your current will always start from the positive side, which is the long side. Okay, your current will actually move in this direction, and you go down here, go through here, go through here, come up here, and end back at the cell again. So your current will just flow all the way through the entire circuit itself. And when current flows through, when your electric current flow through, your light bulb will shine. Okay, you don't need to draw the light bulb, but basically, you don't need to draw the light shining, but basically it's just to tell you, if you close the switch, you have this lamp that shines up. Okay, now if you notice, we also had this resistor here, right? If you think about it, why do we need the resistor? The resistor, the function, right, is to reduce current. Because sometimes if you have too much current, right, it's a bit dangerous itself, your light bulb might actually explode. So because of this, we actually use resistance to actually reduce the current. So there is more of a safe level to use, so you don't actually electrocute yourself or cause any damage to you, to the user itself. Okay, so this is just to make sure that it's safe to use. All right, so next page, let's talk more about current. So just now you have been hearing me talk about electric current, electric current. What exactly is electric current? So electric current is the rate of flow of electric charges. This one, please memorize, must memorize, okay? It's a very, very commonly one-mark definition question that you ask. And the unit for current is amperes. So what we mean by this is, you see all of this? I is current. It's the same as your electric charge. So just remember last chapter, we actually learned about your charge. And then you have your time over here. Time. Okay, so for current itself, current I will be represented with amperes. So the A is for amperes itself. A is the unit. I is the symbol for current itself. Okay, so this formula, right, we don't use it very, very often itself, because there will be another formula later on that we'll be using much, much more often. So when do we use this? Okay, we only if question mentions charge. Okay, only when you have charge, then we use this formula. Otherwise, we don't actually use this formula at all. And if you notice over here, rate of flow of electric charges itself, rate of means divide by time. Flow of electric charge is Q. So it's Q over T. So if your English is good enough, you can actually change the formula from this into the words itself. Can you understand? So you can actually, these two are the same. All right, so your rate of flow of electric charges is your electric current. Okay, now, so electric current is basically how much electricity is flowing in that short amount, in that same period of time, right? So how much current is flowing through my wires. Okay, so how do we measure the current? Because electric current is inside the wire, right? So how can we know what's the value itself? We actually use an ammeter. Okay, and if you notice a ammeter, it measures amperes. So I use ammeter. Okay, and it must be connected in series. So if you all recall back to your lower secondary or to your primary school itself, in series means basically in front or behind any of the component that we want to measure. For example, if you want to measure the current of the battery, I'll put it in front or behind the battery. If I want to measure the component, for example, so this is my component, right? I'll put it in front or behind the component itself. So when your electricity flows through, they're going to be the same. Okay, so the thing is, if you notice over here, if you want to measure the whole entire circuit, we will use the battery. So if you want to measure your total current, we will use the current of the battery. Because you can imagine your battery is like the brain, the power source of everything. So if you want to measure your total current, you have to take it from the battery, which will provide that total current to the rest of the circuit. Okay, so if you want to measure total, just put it in front, and this is technically a cell. So if you all can, just add one more cell in front to make it a battery so that it makes sense. Okay, then over here, you have two different types. Now, if you notice this word over here, this word means default. So if the question doesn't say anything, we always assume that it will be conventional current flow. Okay, your conventional current flow will always be from plus to minus. All right, and we draw your current flow direction right on the wires. We do not draw it along or outside the wires itself. Okay, do take note. Now, if you see electron flow, electrons are negative. All right, and because they are negative, we will start from the negative. So we start from the shorter end. This is what we call your electron flow. So if and only if you see electrons, flow of electrons, transfer of electrons, or just electrons, then you use minus to plus. If not, we always from plus to minus, always. Okay, so just be careful. Now, if you have a closed switch over here versus an open switch over here, so you can just imagine, right, your current, your electric charges, right, they're kind of standing in, like they're queuing up in one circle, right? So if you want to move forward, you have to push the friend in front of you so that you can move forward, right? But if there is a hole or there is a teacher stopping you from moving itself, basically your current tries to move, it gets stopped here. So no current flows through here, so don't have. So it doesn't cause the battery to light up because there's no current flowing through it. This one got current, so it will light up. Can you understand? So you only have current flowing through your circuits if everything is closed and you have a closed loop. So basically, if you take your finger and you do one loop, this is what we call a closed circuit. But if you take your finger, you go to a switch, it goes outwards. This is doesn't go back to the battery, right? So this is not considered to be a closed switch. You must always be able to go back one round to the battery itself. Okay? So it's kind of like a roller coaster, right? Or your water pipe. It must flow nicely in one circle. So same thing, if you have a gap, what happens is, can you imagine your roller coaster? If there's a gap, what happens? Everyone will just fly out, right? So that doesn't make sense itself. You can only start the roller coaster if everything is closed, everything is safe, there's no breakage or anything like that. Okay? So next page, let's talk about your word example. So now read the questions carefully. They ask you to draw and you want to measure current. So you want to measure current, first thing is I need my ammeter to measure current. Okay? And it is through a light bulb. So you need to use ammeter to the light bulb. So they tell me I use a switch, I use a cell, I use a resistor itself. So I also mentioned this. All right. So if the question ever asks you, how come you put in an extra resistor, you can tell your teacher, it's actually to protect my light bulb. Otherwise, my current is too big, it might cause the light bulb to explode. Okay. So first things first, we always draw the battery, the cell. Okay. This is your power source, so we always draw it first. So to make things simple itself, first thing, your switch, right? Now, your switch will always be placed in front of your battery. It is just a, how to say, it's just a good habit to have, because basically your positive part of your battery, right, is the most dangerous part. So you want to put your switch in front of it so that you can control whether the dangerous part is on or off or not. Okay, so don't worry too much about this. When we reach nearer to the end of basically your third chapter of electricity, fourth chapter, sorry, of electricity, then you understand why you need to place a switch in front. So for now, just make it a habit to always put the switch in front. So next, you want to have a light bulb. So this is your light bulb, right? And don't forget, because I want to measure your current of this light bulb, so I'll put the ammeter right next to it or in front of it. Okay, then what happens next is they want a resistor. So a resistor just looks like a rectangle. So do take note, the line should not cut through the resistor. So double check. I have a switch here. So just in case, because we are gonna, this is a drawing, right? So you might want to label it as well. You have a cell, you have a cell, you have a switch, you have your light bulb. Okay, because the question says light bulb, I will use the word light bulb. You have your ammeter, and you have your resistor over here. Okay, so with this, you have all of your individual components, and this is how you get your 3 marks. So yes, it is a bit tedious, but once you get the hang of it, it will actually be very, very simple. And if you notice, I drew it freehand, right? But as much as you can, always grab a ruler and draw your wires, because wires are very, very straight, and try not to have any gaps in between any components. Because remember, if there are gaps, what this means is now your circuit is not closed. So if your circuit is not closed, what happens is you can actually not be able to conduct electricity. The current cannot flow through. Okay, so as much as you can, try to use a very nice ruler so that you draw it properly, something like this. Okay, but that one didn't label it, so they might minus marks. Because you see 3 marks, right? You just want to play it safe. Just in case your teacher likes to minus mark from you, just don't give them a reason to minus marks from you. All right. Now this one over here, it should be 0.60. Okay, now I'll explain why am I so picky about it later. So they want you to find your ammeter reading. Ammeter is for current, right? And they tell you you have your charge Q, and they tell you you have your time over here. So first thing, ask yourself, my charge is this. Okay, my time is 1 minute. So the thing is, when I'm gonna use a formula, okay, I is Q over T. When I want to use a formula, always make sure that we are using SI units. So ask yourself, is coulombs SI units? Yes. Is minutes SI units? No. I need to change it to 60 seconds. So now all the values are there. All I need to do now is throw in my numbers. So over here, you end up with 0.010 amperes. And if you notice, I put 10, right? Because we try to always leave your answer in 2 or 3 SF. Okay, so in this case, we don't actually need to show it, but if you need to, just write 2 SF. In this case, we don't leave our answers as a 1 SF value answer. So if you have a very nice number like 1, 2, or whatsoever, write 1.0, 2.0, because some schools are known to be stricter, and if you don't follow accordingly, they'll minus 1 mark from you. So to avoid that, we always try to put 2 or 3 SF at the end of all of our final answers. Okay. Next one, over here, they tell you now I have a charge here. This is Q. Calculate the number of electrons. So nothing to do really with your, how to say, have nothing to really do with your current as well. Because you see, the moment you see number of electrons, we didn't learn about electrons at all, right? So basically, this is just a number game. It's just maths right now. So what I mean by this is your total charge is 0.60, right? The charge of 1 electron is this very, very small number. Okay, if you never notice, this is 10 to the power minus 19. It's extremely, extremely small. So you want to see the number of electrons. So all you need to do is just take total charge divided by charge of electron. So I'm just going to take 0.60 divided by this very, very large, sorry, very, very small number, not large. Okay, so if you do 60 divided by 3.6 times 10 to the power minus 19. And because you notice there's a times below, right, it's a good habit to always put a bracket so that at least you don't make any mistakes. So you end up with 3.75 10 to the power 18, right? So there's a lot of electrons itself. So normally for physics itself, we are not too concerned about the number of electrons. We leave that to the chemistry parts. But basically, yes, there are occasional times where questions can ask you about it, but they'll probably give you the number. So you just need to understand how much electrons do I need to add up all my charges to give me 0.60. That's what that question is asking for. So if you notice over here, all your values here are 2SF, 2SF. So my final answer, I should also try to keep it as 2SF as well. Okay, this is just a habit itself. It's good habit. So if all parts of the question is 2SF, 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 try to leave your answer in 2SF also. If you have 2 and 3SF, basically we'll use 2SF. We always use the smaller one. But if all the answers or all the values in the question is 3SF, 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 then leave everything 3SF. It's just a habit because when you move up to higher education itself, they also put this or implement this as well. Okay. Now next part, you have your current, which is this value, and do take note this is kiloamperes, and you have time. Okay, and they ask you to find number of electrons. So basically, question 2 is just the combined version of B and C. So first thing you want to ask yourself is, now I have current. Okay, I'm going to write this here just in case. But once you guys understand already, you can just write I equals to whatever value. And because we are going to use a formula later on, we need to change everything to SI unit. So just like your kg and whatsoever, this is just times 10 to the power of 3. Okay, it's the same as 3 zeros. Then next, you have your time, right? And this is 12 milliseconds. So 12 milliseconds itself is divided by 1000 or times 10 to the power minus 3. So you end up with 0.012 seconds. So do take note of the milli itself. Okay. So we have this. Next step is we know I is Q over T. The question is asking us for Q. So we manipulate it. We move the T up. So Q is I times T. So we have 30,000 times 0. Okay, give me a second. 0.012. Okay. So let's press the calculator. 30,000. You get 360 coulombs. Okay, don't forget your units itself. So you can see at the end of every equation, I will write the units. All right. So next step is you want to find your total number. Okay. So our total Q is 360. However, each of them is 1.6 times 10 to the power of minus 19. So press this in your calculator, 360 over, remember, because this is a multiplication, I will put a bracket below, just in case. So you end up with 2.25 times 10 to the power of 18. No, sorry, it's even bigger. It's 201. Okay, and if you notice over here, you have 360. 360, you can treat it as 2SF or 3SF, but the 1.6 below is 2SF. So we will round up our values to the smallest. So we'll put 2SF here. Okay, this one is just to play it safe. So don't just only write this part out, write the one on top as well, so that your teacher can understand why you need to use 2 or 3SF accordingly. Okay, so some teachers are nicer, they'll just let you know if you need to do this step or not, then they'll still give you the marks. Some schools, if you don't show this step at all, they will actually just penalize straight away. So do take note, for electric current itself, this formula, even though in the word example we have been using it quite a bit, we don't actually use this very, very often for the whole electricity chapter itself. These are quite rare. Sometimes it's only in MCQ only. So you still need to know the formula, but what's more important is actually the definition itself. Okay, and then your ammeter, where should you place it? Your 2 different types of current flow, and basically that is it for your current. It's not a very, very troublesome part, but for electricity, there's a lot of things, there's a lot of formulas to memorize, there's a lot of definitions to memorize and understanding as well. So this is one of the harder chapters for electricity. So if you need to stop and take a break, feel free to do so. So if you are revising, try not to do it one shot sometimes. So do it bit by bit. Maybe you just do current first. Later we'll learn about your voltage and your resistance. Do it step by step. Maybe every day you just spend like 5-15 minutes just to go through each and every component to revise itself.